Okay, if you hear something like a big radial saw cutting through pipes, it's actually happening right now, right outside of the office. Now, very, very good job. This was actually a pretty complicated one. Now from an intuition, I'm not entirely sure on how to solve the type of exponential equations that we have in section 1. So it was very good. And now let's get into business. So, one, 3, and 5. I'm going to show you all 3 in once because there is something called limit hierarchy. That I want to talk to you about. If x tends to infinity, then we have the following. The idea of infinity is not exactly an infinite amount when talking about functions. When talking about functions, the infinity refers as to how fast the function increases. So in the infinity, the fastest function is x in power x. This gets ridiculously large, ridiculously fast. This is much larger than the factorial of x. This is much larger than any exponential. This is much larger than any polynomial. No, not really. This is much larger than any root, and this is much larger than the logarithm of x. If x tends to 0, this hierarchy is completely reversed, because if x tends to 0, there is an array of different problems that appears, but we'll actually see some of those. So first limit for number 1. So let's use our hierarchy here. I'm going to type here how fast. There you go. And so using that, who can tell me the value of this limit in less than 10 seconds?
Plus infinite?
No. This limit is 0. If you look at this function tends to 0 super fast. So we have a polynomial against an exponential. So the polynomial doesn't really have any role to play here because the exponential goes to their limit much faster. Now, number 3. Now, another 10 seconds. What is the value of this limit?
Isn't it 2?
It is 2 indeed. The reason is exponential in the numerator, exponential in the denominator. They have the same base, they have the same exponent, so they grow exactly at the same speed. This is the exact same case as when we had quotients of polynomials. The value of the limit is this beautiful thing over here. Now, for the third and last of these limits, we have this thing over here. It looks hideous. It looks terrible. I mean, it has a logarithm on it. It's kind of the thing. Why is the value of this limit and why is it minus infinity? Once again, I'm going to show you the figure. This is 1. When x goes to 0, this order kind of reverses. And so the logarithm of x is one of the functions that go the fastest to 0. The vertical axis serves as a vertical asymptote, but this growth here is exponential, so it's pretty damn fast. It goes to minus infinity so fast that the x doesn't know what to do, and so it's the logarithm that rules. Now, questions about the speed at which functions grow. What is after x in power x? The next function that grows the fastest is the factorial. And this is x times x minus 1 times x minus 2. This beautiful thing over here is the factorial. Now, moving on. Next thing we have for today are the inverse trigonometric functions. And we start with a simple one. Here, writing this, the arc sine or sine in power -1, it means x equal sine of y. So we're going to call this x, for example. This is an arc sine, and so what we know is that square root of 3/2 is the sine of x. Now, who tells me an angle whose sine is exactly square root of 3/2? Pi thirds. Okay, who gives me another? Fair enough. I'm gonna give you the full set of solutions. This can be but there's another angle that has sine equal to square root of 3/2, and that's 2 pi thirds. So this is the solution to this equation. When you're talking about sinus, cosinus, tangents, and all that, you have always to consider that you'll probably have an infinite family of solutions, and sometimes even more than one. Exactly, Philip. So if we want to visualize it, this is the upper half of the goniometric circle. This is the angle. Something like this. Now, next. Next, we have number 3. And that's arctangent of -1. Quick, 2 solutions. What's the angle that has tangent equal to 1? Pi fourths plus what? What's the period of the tangent function? sorry. Exactly. The tangent function has period pi, which means every half a lap, the sign of the tangent remains. Yeah. Now for number 7. Now, who is going to say in the exam that the solution of this is 2 pi thirds, and why will we give them only half points?
Because you're not taking into consideration the domain of the function.
That's interesting, but it's not why. Okay. In before, the domain of the arctangent is R. Like you can wonder about an angle whose tangent is worth anything really. So we have no problems with domain. The thing here is that tangent minus 1 and the tangent are inverse functions. So if you want a solution in the interval 0 pi over 2, sorry, 0 pi, then your answer will be 2 pi thirds. However, if your answer has to lie in R, there are many angles whose arctangent is the same tangent as 2 pi thirds, and that's all angles who have the same tangent as 2 pi thirds. So we just let the goniometric circle revolve, and each time we do half a lap, we mark a new angle because they have the same tangent. Like, and this is like the easiest trap ever. Please don't fall into this. Please don't forget to include all solutions to the equation. Now, before we solve number 19, I'm going to show you something. In order to see how this works, I'm going to derivate this, and I have 1, and I have 1 prime cosine y. So y prime is 1 over cosine y. Now I'm using the following identity here. I told you we would see it again. So y prime is 1 over square root of 1 minus sine squared of y. And what is this? X. So yeah, the derivative of the arc sine is 1 minus x, 1 over square root of 1 minus x squared. And now we're going to use it. So exercise 19 asks us to calculate the derivative of sine minus 1 of 2x minus 1 over 3. And this is derivative of the arc sine minus 1 times the derivative of this castle, which is 2. Questions about derivating the arc sine? I'm going to write it here. These are the derivatives of the arcs. I think they're visible. Yeah, kind of. I need a new pen. Now I'm going to show you number 33. If there are no more questions. Our curve says tangent minus 1 of 2x over y is equal to pi x over y squared. So now we have to strong arm this and derivate it as it is. So let's derive the first side. We say 2x over y is equal u. And so the derivative of the first side is u prime over 1 plus u squared. And this is u prime. So our derivative here is 2y minus 2x over y in power 4 divided by 1 plus 2x divided by y squared. Now, for the other side, did I do this correctly? No, I didn't. Much better. Now, for the other side, in the denominator we have y in power 4. And here we have pi times y squared minus pi x, derivative of y squared, which is 2y prime. So we have this little monster over here, that is the derivative, and y4 is y squared squared. So this equation apparently tells us how the derivatives work. So let's do some transformations here and see what happens. First of all, these two gentlemen over here have the immense kindness to cancel each other out. And so we have 2y minus 2xy prime. And here I'm going to unravel this already. And we have y squared plus 4x squared divided by y squared. And here we have pi y squared minus pi times 2xy prime. This is dividing the denominator. So it goes out multiplying y squared. That multiplies 2y minus 2xy prime. Y squared plus 4x squared is equal to pi y squared minus pi 2xy prime. Now, what do we do from here? Okay, this equation looks a little bit bulky. There's still some things we can do. We can cancel one y here with one y here and one y here. And now I'm going to delete the hierarchy of limits with much grief. Good. And now we replace. We want to calculate the slope of the tangent in the point 1, 2. We already have an equation that relates x, y, and y prime. So here we replace y with 2 and x with 1. And we leave the slope as it is. 2 squared plus 4 times 1 squared. This is pi times 2 minus pi times 2 times 1 times y prime. So now we put all numbers together. We have, this is 8, so it simplifies with the 2. We have 4 minus 2y prime, and this is 2 pi minus 2 pi y prime. So now we move the y primes in one side and the numbers in the other side. And so with this, we get a very nice first degree equation. This is 1 minus y prime over 2 pi minus 2 pi y prime, which we can transform. This thing goes here, this thing goes here, and we have y prime that multiplies 2 pi minus 1/2 is 2 pi minus 1. Fair enough. With this, we have that the slope is 2 pi minus 1 divided by 2 pi minus 1/2. No, this is the typical moment when you start doing equations and forget what you have been asked for is exactly here. Because we have a pretty bulky equation with x, y, y prime. This is a full-fledged ODE. Actually, if you wanted to solve it, the solution would probably be something this way. And here, where we really don't know much about what to do, is when we have to read the problem again. And then you see, find the slope of the curve, which is y prime, at the point 1, 2. Okay, the point 1, 2 means x equals 1 and y equals 2. So we put the point into the equation and we get the slope. I love these exercises that look so cryptic in the beginning and then first degree equation. Beautiful. Anyway, 10-minute break. We start over at 11:10. So yeah, good observation. Thank you, Jonathan. Now let's move on. Now, so now we're moving into second order differential equations. We have this thing over here. The way we solve it is we calculate the characteristic polynomial, and then depending on the solutions we get, we will have one result or another. So let's see. The characteristic polynomial is lambda squared plus 10 lambda, plus 7 lambda plus 10 equals 0. The roots of this are -7 plus minus a square root of 49 minus 40 divided by 2. They're both real. This is -7 plus -3 divided by 2. So either -5 or -2. And since these values are both real, then the solution is something like a in power minus 5t plus b e in power minus 2t. Questions about second order ODEs? Good. You have no questions. You know how to calculate the characteristic polynomial. The book here uses R. I like to use lambda because this is what these two are called eigenvalues of the equation, and these actually are called eigenfunctions of the question. And notation for eigenvalues is always lambda. So that's why I like to use it, but the book here uses R. That's good as well, as long as you have very clear that this characteristic polynomial is built with as much degree as the derivatives you make. Y second, lambda squared, y prime, lambda first, y nothing. Now, I'm going to show you number 7. It says y second minus 6y prime plus 10 y equals 0. Same thing over again. Characteristic polynomial. Lambda squared minus 6 lambda plus 10 equals 0. So lambda is 6 plus minus the square root of 36 minus 40 divided by 2. This is 6 plus minus the square root of minus 4. Okay, here we already start having some trouble. This discriminant is negative. What does it mean? Okay, I'll show you. This is either 3 plus I or 3 minus I. So, if I remember correctly, the solutions here use the entire part of the complex solution. Good. So, the solution to this is e in power t in power the entire part times a linear combination of sine of cosine of t with the imaginary part. So this is e in power 3t A cosine t plus b sine t. There's an absurdly high amount of intricacies to this result, but main idea is the real part of the eigenvalue goes to the exponential, and the imaginary part of the eigenvalue, which in this case is a 1, goes to the cosine and sine. Oh, wait, no. This is not true. Now, much better. Here, this is a real parameter, this is a real parameter, and same thing with this. Now, questions about solving second order linear differential equations? No questions. Okay. In that case, congratulations. You just saw an application of linear algebra. Now, moving on. Next, a classic, an all-time classic. Initial value problem given by 2y second plus 5y prime minus 3y equals 0. Y of 0 is 1, y prime of 0 is 0. So, first of all, let's solve this equation. Characteristic polynomial is 2 lambda squared plus 5 lambda minus 3 equals 0. So, this is y. Lambda is minus 5 plus minus square root 25 minus with the minus plus. That's 6 times 4, 24 divided by 2a. This is minus 5 plus minus 7 over 4. So this is either minus 3 or 1 over 2. Okay. So our solution is a e in power minus 3t plus b e in power t halves. Now, we apply the first condition. from first condition, we know y0 equals 1, and that means this is 1, this is 1, so a plus b equal 1. Fair enough. And now I'm going to derivate the equation y prime. We have minus 3a e in power minus 3t plus 1/2 b e in power t halves. And now we are applying initial condition number 2, which says y prime of 0 equals 0. This means this becomes 1, this becomes 1, minus 3a plus 1/2 of b equals 0. And this is a 2 times 2 linear system. So let's solve it. We have a equal 1 minus b, so minus 3, 1 minus b plus 1/2 of b equals 0. This is minus 3 plus 3b plus 1/2 of b, that's 7/2 of b equals 0. So b is 3 times 2 divided by 7, which is 6/7. And thus a is 1 minus b, which is 1/7. So, conclusion from all of this. We know the value of our two constants, so our function is defined by 1/7 a in power minus 3t plus 6/7 e in power t over 2. Now, this one was pretty hectic, so if you have questions, it's time for them. It seems quite straightforward. It is quite straightforward. You only have to be systematic. Solve the equation, find the constants. And this is it. Now in this part, most of problems are actually initial value problems. So I don't really think there is much value into solving many more of them. So we are going to move into the next one. Can you give us real life of the usage of differential equations? This is the equation of a spring, probably. Like this type of second order linear ODEs usually model things like springs, rubber bands, and other type of elastic efforts. It's pretty common that you have complex eigenvalues here, and that's what happens when you release the spring, and it kind of wobbles a little bit. That wobbling equation is described in somewhere similar to this with sines and cosines. Okay, part 4.1 apparently seems to be dedicated to some simple real life applications. I'm going to cover a couple of them as well. And hopefully we'll find something interesting. Let's go. 4.1.1. It says find the change rate of area. Okay, so we know that the area is a function of time, basically. Now, the initial length of the side of the square is 8 centimeters, and we know that duration of L with respect to time is 2 centimeters per minute. This is what we know. This is all data the problem gives us. And now I'm going to give you an additional piece of data that I probably shouldn't, but it's important to solve the problem. The area is the side square. What we want to find in this problem is the variation of area with respect to time. So let's replace this thing here. Now, if this looks like a derivative to you, it's because it is. So let's solve it. This is 2L derivative of L with respect to time. And this is 2L times 2, which is 4L. Okay, this makes sense. This makes a ton of sense. As if you think of this is a parabola. And now what you're looking for is the rate of change of the area. So is this correct? Yes, it is. Thank you, Iris. So change rate. The change rate of this square at any given moment is actually the perimeter of the. How did I differentiate? This is the square of function. We know that the side changes with time. I mean, we have it here. And so since this is a function of t, the derivative of the square of the function is 2 times the function times its derivative. This is implicit derivation. All right, let's do one more then. Okay, I'm going to do number 15. So we have P, a point, X, T, Y, T. Sorry. X, P, Y, P. So that's that. At each time T, so it verifies all these equations. Xt, yt equals t, and yt equals xt squared. Okay. So let's see what we can do here. So from here, yt is t over xt. We move it here, and what we have is that xt cubed equals t. So so xt is t in power 1/3. And from here, we move it to the equation above. And we have that yt is t over t in power 1/3, which is t in power 2/3. So our point P of t at any point t is in the position t 1/3, t 2/3. Now, questions about this? Good. Then let's move on. We want to find the change rate to the distance of the origin. Now, what is the distance to the origin? Well, the distance to the origin of any point xy is x squared plus y squared, but the square root of that, this thing here. So in our case, the distance from P to the origin is the square root of t1/3 plus t2/3, both things squared. So it's equal to the square root of t in power 2/3 plus t in power 4/3. Now, how do we calculate the variation rate of any given amount with respect to a variable? We derivate it. Got them. Let's go. So the change rate is the derivative with respect to time of the distance, obviously, is the derivative with respect to time of the square root of t in power 2/3 plus t in power 4/3. Now, what is this? This is this thing over here in the denominator, and in the numerator goes the derivative of what is inside, right? Which is 2/3 t in power minus 1/3 plus 4/3 of t in power 1/3. So now let's see if we can figure something out. This 2 cancels this 2, and this one becomes a 2. So this is t in power minus 1/3 plus 2t in power 1/3 divided by 3, because these 3 didn't cancel. Now, you may be tempted to substitute t equal to here. And what you would get is the distance to the origin at t equal 2. However, what you would not get is how fast the speed changes at t equal 2, which is the reason why you have to derivate this. So this is the rate of change. This is the distance. This is the rate of change. You solve whatever this number is, and that's the rate of change. Again, if you substitute here, you don't get the change rate, you get the position. Now, further questions. This type of exercise are generally incredibly straightforward, but you have some manipulation to do with the variables first to try and understand mathematically what is actually going on. That's the fundamental difficulty, that sometimes it's phrased in such a way that may lead to confusion. which, for example, may be the case here. All right. Then let's do the last one. And we can call this a day. All right. Okay, number 18. We have the situation. And this is being pulled at 1.3 meters per second. Yeah, that's basically what the exercise is. Now let's see. First of all, we have L here, and we know by the Pythagorean theorem that this is true. And we have that, which, if I remember correctly, is 3 point something. Good. So initial position of the top of the ladder. This thing over here, a number, a beautiful number. So if you drag the stair, oh, hell, no, this is not true. I lied to you miserably. This is Y, this is X. Initial position is actually 5. This is what happens when you don't read the exercises properly. 5 meters. Initial X, 0. What is the relation between these two? X squared plus Y squared equals 5 squared. Pythagorean theorem, 101. There is no way to run from it. You know, the angle in the wall is always straight. So we know we know that these things changes with time. So we know that x depends on time and y depends on time. Next data, we are pulling it away. So horizontal speed is 1.3. And now we could possibly come here and derive this and find the position rate of y. So let's see. We derivate this. And we have 2x dx dt plus 2y dy dt equals 0. Now, x and y are functions of t. So when you derivate them, the derivative appears here. Now we know that this is fixed. This is fixed. So we have here, 2,6x plus 2y dy dt equals 0. And so dy dt is 1.3x divided by y. Minus, because it goes downwards. This thing goes subtracting to the other side, 2y divides, and since this looks kind of even, this looks kind of even, I just divide it because it's a decimal number and decimal numbers just don't care. Now, we have the change rate of y, the speed at which the height of the stair drops. Now, we have been told, second part, that y equals 3 meters. Okay. If y equals 3 meters, you know, the stair is 3 meters above the edge of the wall. We use this relation. So we have x squared plus 3 squared equals 5 squared, from which x equals 4. So x is 4 meters away. And now, what did we need to calculate the change rate of the height? X and y. We solve it. Here, the change rate of the stair is minus 1.3 times x divided by y. This thing. And that's approximately minus 1.73. So the stair is falling pretty damn fast. I mean, the poor construction worker that is sitting, for example, over here, is definitely going to have a bad time. Now, questions about change rates. Good. Then I'm going to check assistance and we can call this a day.